In this video, we derived the material derivative. We start with a review of derivatives and partial derivatives, and that leads on to our discussion on material derivative. So let's start with the derivative of a function of a single variable. You are very familiar with these derivatives, so let's consider a function. This function could represent the temperature as a function of space. I call my function g. And let's say that we look at a particular point along the graph of this function, which is at point x naught, and the value of the function is then j at x naught. Now, why do we care so much about derivatives? Well, that is because oftentimes we care a lot more about how the function is varying than the value of the function itself. So take the GDP of a country, for example. You may not care so much exactly about the value of the GDP, but you do care a lot about the growth rate. And the growth rate is the derivative of the GDP with respect to time. So since high school, you know that the derivative is the slope of the line which is tangent to the graph of your function at this point. And there are different ways of writing the derivative. We can write it as j prime. Usually in engineering, we specify with respect to which variable we differentiate, so we write it a dj dx. And so the value of the derivative really tells us how fast does the value of my function g changes when I move along in the x direction. Now, the value of the derivative is also very strongly linked to something else, which is the linear approximation of g. The linear approximation of a function simply means that if we look in the neighborhood of a function, for example here, then the value of the function, which is the black graph here, is almost the same as the linear approximation at the point x naught, which is the red line here. So let's say, for example, then I know the value of my function at x naught. What is the value of my function if I move a delta x along the x-axis? Now I know that the value of my function is g at x naught plus delta x, but really this value is almost the same as if we approximate it by the point which is on the red line. That we can see in a Taylor expansion. So we know that g at x naught plus delta x is almost equal to the value of the function at x naught plus the derivative of the function at x naught times delta x. Now, why is that a linear approximation? Simply because we can now write the change of the value of our function, delta g, as a function of the size step I took in the x direction, delta x. And that relationship is linear. Delta g is equal to an alpha times delta x. And that alpha is precisely equal to the derivative at this point. Now, what happens if we have a function of several variables instead? This is a function of several variables. Let's say, again, it represents temperature, and that curve here is the graph of my temperature. I will again call my function g. This function is now a function of two independent variables, which are x and y. So let's say I'm at a point here, x naught, y naught. At every single one of these points, I can measure the temperature, and the value I can read from the graph of the function. How fast does the temperature change now? You see immediately that you don't have enough information. We need to know in which direction in the xy plane we're moving before we say how the function varies, how the temperature varies. If we decide to move in the x direction, and that means y remains constant, and we move in the x direction, then the value of the function is going to follow this line here, and we directly see that the temperature decreases when we're moving in the x direction. If we now move in the y direction in the plane, then we can read from the graph what happens with the temperature. And we see here that the temperature is now going to increase. So for function of several variables, we cannot define a single derivative which is going to tell us how the function varies. For this function of two variables, we need two numbers. We need to know first how the function varies in the x direction when y is constant, and that is the definition of the partial derivative of g with respect to x. This partial derivative tells us how fast the value of g changes when we are moving only in the x direction. We also need to know how the function g varies if now we're moving along the y direction and x remains constant. And that is precisely what is represented by the partial derivative of j with respect to y. Here, x remains constant, and this number tells us how fast does the value of g change when we're moving only in the y direction. So where for function of single variable, we just needed one derivative, you see directly that for a function of two variables, we actually need two derivatives. And we call them partial derivatives because we always need to keep one independent variable constant. If you put these partial derivatives in a vector, because they have two components, this is exactly the gradient of g. Now, just like we could build a linear approximation with the derivative of the function of a single variable, we can build a linear approximation of our function of several variables by using the partial derivatives. So if we look around our point here, the graph of the function is going to remain really close in the neighborhood to the plane which is tangent to the graph at this one point. And the linear approximation tells us how our function g varies. So what is the delta g by which the function will increase or decrease if we take a step delta x in the x direction, and if we take a step delta y in the y direction. Now let's say for a second that I'm taking a step delta x in the x direction and that I'm not moving along the y direction such that delta y here is equal to 0. I'm focusing only on this point here, then delta g is equal to alpha times delta x. And what is alpha? Alpha is then precisely the partial of g with respect to x. That tells me how fast g changes when I take a step delta x in the x direction. Assume now we take only a step in the delta y direction, so delta x is equal to 0. Delta g is now equal to beta times delta y, and beta tells me how big is the change of delta g when I'm taking a step delta y in the y direction. Well, that is precisely the definition of the partial of g with respect to y. So if we know the value of the partial derivative, we can build a linear approximation for our function g. It's important to note here that in this expression, I am explicitly saying that I can move as much as I want in delta x and as much as I want in delta y. That is to say that x and y are independent variables. So let's move on to fluid mechanics now, because there we are also very interested in how functions vary. But when we look at transport of internal energy or temperature, transport of mass, or transport of momentum, there it is easier to think about how these vary when we are following a fluid element. Say, for example, I have a velocity field, a flow field. I might be interested in how the temperature varies when we're following a fluid element. Now, what does that mean for the derivative? So let's say that this here represents the temperature around our wing profile. Remember that I'm only moving in the xy plane, and the value of the function here is not on top of the velocity field. This graph here only simply indicates the value of the temperature at a specific point. Now, what I want to know is how the temperature varies as a fluid element moves along this wing. If I want to compute this, you directly see that x and y are no longer independent variables. I cannot choose a random step delta x and a random step delta y and then still hope that I moved along a streamline. The two variables are now no longer independent. So how can I characterize the variation of my function as I'm following a fluid element? Now, this is precisely what the material derivative represents. Here is the question we ask. How does the value of g change when we are moving with the flow? Assume we are at this point and we follow a material element as it moves along with the flow for time delta t. How would the value of the temperature have changed over the time delta t? So what is delta g? Now, g is still a function of several variables. It's a function of time, of x, and of y. So I just wrote the linear approximation for the function g for the function of two variables x and y. But I could do the same for a function of three variables, t, x, and y, and delta g would be equal to the partial with respect to time times delta t, plus the partial with respect to x times delta x, plus the partial of g with respect to y times delta y. But when I'm writing this, I'm assuming that I can take a delta t, a delta x, and a delta y independently. If I'm following the flow, I cannot do that. So let's consider a time interval delta t. When we move with the flow, delta x and delta y are no longer independent variables. In fact, we know that if we are following the flow for delta t, then the fluid particle has to end up precisely there, and that would be only a function of delta t. So how can we find the delta x and the delta y by which a fluid element has moved in delta t? This information is given by the velocity vector v at this one point. It has two components, u and v, and the distance delta x traveled in the x direction over delta t is simply u times delta t. The distance delta y traveled in the y direction over delta t is simply v times delta t. I can now substitute these expressions into the expression of my linear approximation, and I get that delta g is equal to this expression here. And it's important to note here that the only independent variable now is delta t. I can factorize this delta t and simply write that delta g is a linear function of delta t, and my derivative is now this number. That is what we call the material derivative. It is usually written with a capital D, capital DT. So the material derivative tells us how the function g changes if we were able to follow a fluid element.